Good day, students. Today, we are considering a topic titled Sonometer. The frequency of the note produced by plucked string can be studied with the use of an equipment called sonometer. It consists of a hollow sounding box with a straight wire along its length. The length of the vibrating part of the wire or string can be varied by adjusting the movable bridge B. The length of this vibrating part, is smaller, there will be higher frequency to vibrate fast. For example, frequency is inversely proportional to the length, equals to K over L. If the length is 2, for example, 2 meters, we want to know the frequency. It will be 1 over 2, for example, which is 0.5 hertz. Now let's try when the length is 5 meters. Frequency will be 1 over, let's say, 5, which is 0.2 hertz. See that the frequency, when the length increases, the frequency will reduce. Now, let's see how it can be shown. This shows that the frequency of a vibrating wire is inversely proportional to the length, directly proportional to the square root of the tension, and inversely proportional to the square root of the mass per unit length, represented by a capital letter M, in which the unit is kilogram per meter. Mass per unit length. The unit of mass is kilogram, the unit of length is meter. While the unit of M, capital M, is mass kilogram per meter. Now let's continue. The three important relations combined here is to F to be directly proportional to tension, inversely proportional to the length, and inversely proportional to the square root of the mass per unit length. That is directly proportional to the square root of the tension. When you remove the proportionality constant, introduce your K. F equals to K over L square root of tension over mass per unit length. The unit of mass per unit length is kilogram per meter. The mode of vibration for the fundamental mode of vibration, K equals to half. F naught equals 1 over 2L square root of tension over mass per unit length. In this case, it's still applicable to this string, plucked string. I said L equals to lambda over 2 under plucked string. It's still applicable to sonometer because sonometer makes use of string. And you can see the 24 placed at this point on top of the stretched vibrating part of the string. When you sound this 24, it will transfer its own natural frequency to the wire being stretched by hanging this weight. There will be resonance. Resonance will take place. What's resonance? A system is said to be in resonance when the external force share the same frequency of its natural frequency. See, this is the external force placed on this wire. It shares its natural frequency with the vibrating wire, so that the sound produced here, it will be transferred to this grid to now have similar frequency with the sounding 24. Now, it will make use of what we have in the stretched string, which is the first loop, L lambda over 2 which is L equals to lambda over 2, as we said before in our previous lesson. Lambda equals to 2L. Your V equals to F naught lambda. F naught equals V over lambda. Replace your lambda with 2L. V over 2L. Now we are going to make use of the same thing. When you have vibration here, you have the first one will be lambda over 2, the loop. When it vibrates, it gives us the fundamental frequency before the other loops be coming up. That means that under sonometer, as we have under string, clock string, we have F naught, 2F naught, 3F naught, 4F naught, 5F naught, 6F naught, combination of odd and even number. Also in sonometer, we have the same similar combination of odd and even number. In sonometer, we have F naught, the way we have in string, 2F naught, 3F naught, 4F naught, 5F naught, 5F naught, etc. and so on. The first one is your fundamental frequency. Fundamental frequency. While the second one is your first overtone and or second harmonics. The fundamental frequency or first harmonics, as we have in the clock string, the same thing because we are making use of string here. This is third harmonics or second overtone. Third harmonics or second overtone. Third, fourth harmonics or third overtone. Fifth harmonics or fourth overtone. How do we get that? Under sonometer, your F naught equals 1 over 2L square root of tension over mass per unit length, which is your equals to fundamental frequency. For the first overtone or second harmonic, you have 1 over L square root of tension over L, which is 2F naught. It combines two of these together to give us this. This is equals to second harmonic or first overtone. How do we get it? When you add 1 over 2L plus 1 over 2L to give us 1 over L, 1 over 2L plus 1 over 2L, which is 2L, 1 plus 1, which is 2 over 2L, 2 cancel 2, which is 1 over L. That's 2F naught combination. Combine this. If you have F2, which is 1, you add 1 over 2L, you pick 1, but you leave this V. 1 over 2L 3 times. You have 1 over 2L plus 1 over 2L plus 1 over 2L. LCM is 2L. That's 1 plus 1 plus 1. When you add it, you have 3 over 2L. 3 over 2L. That means that the F2 will now be 3 over 2L square root of tension over mass per unit length, which is 3F naught. Combine this one 3 times to give all this. That means that this one is 3 circles. 3 circles. That is, you have something like this, 3 loops to give all this. This one will be 2 loops. You have 3F naught, which is equals to third harmonics or second over turn. That's it. It's combination under string. Sonometer, you have F naught, 2F naught. Under sonometer, you have F naught, 2F naught, 3F naught, 4F naught, 5F naught, etc. Combination of odd, even, the way we have in the stretch string. Please take note of this. The stretch string vibrating, the frequency of a vibrating stretch string or wire depends on 3 factors. You can be asked in your exam. Depends on 3 factors, depends on the length of the string, it depends on the mass per unit length, capital N, and also it depends on the tension. You can see it depends on the tension, mass per unit length, and depends on the length of the string. This is the end of our class. Please subscribe to my channel so that I can have access to the latest video. Have a wonderful day.